Welcome back, everyone. So we'll resume our sessions for this afternoon. We have Professor Said Hamdioui. So, Professor, we are very excited and honored to have Professor Said Hamdioui with us, join us in this conference. So, Professor Said Hamdioui is currently Chair Professor on Dependable and Emerging Computer Technologies and Head of the Computer Engineering Laboratory in the Delft University of Technology in the Netherlands, where he also received his Master's of Science in Electrical Engineering and his PhD degrees with honors. He's also currently co-founder and CEO of Cognitive IT, a startup focusing on hardware dependability solutions. So prior to joining TUDelft as a professor, Professor Hamdioui worked for many companies such as Intel in California, Philips Semiconductors R&D in France, and Philips NXP Semiconductors in the Netherlands. Professor Hamdioui has consulted for many worldwide semiconductor companies in the area of chip testing. He has also a high record of research and a distinguished record of research publication with over 250 research papers, where he focuses on dependable CMOS, nanocomputing, and emerging technologies and computing paradigms. We are very excited to have Professor Hamdioui today. And his story is very inspiring to all of us, and hope you enjoy his story. So the talk that will be given us today is about computation in memory for edge AI, opportunities and challenges. A very interesting topic, and hope we learn a lot from him. The virtual floor is yours, Professor.
Good afternoon, everybody. Good morning, good evening. It depends where you are in this globe, in this world. Once again, thanks, Hisham, for the nice introduction. It's a pleasure to share with some of my thoughts and my ideas and some of the work that my department has been doing in the last, 5-6 years when it comes to new computing paradigms. At the moment, I am actually located in Nador, sunny weather, 20 degrees, very exceptional. Arriving yesterday, just evening from the Netherlands, where it's freezing, temperature below zero. So I'm really enjoying the sun while giving this talk online. So what I would try to do in this talk to explain to you another aspect which is not really much addressed. For sure in Europe and also for sure in Morocco. When we talk about AI, which is now a revolution, most of people, to be politically correct, most of people think about algorithmics, data analytics, trainings, models, etc. But we usually forget about a fundamental component in deploying AI, which is the computing platform. And we'll understand that we really have major challenges ahead of us when it comes to developing radically, I'm saying radically new computing paradigms, if we really would like to deploy AI at large. What I'm saying AI at large is deploy AI at the edge, where the data is generated. For instance, why not having a wearable device which monitors your health 24 hours a day, 24 hours a day? It's kind of working based on a battery, and you don't need to change the battery every day, but you change it, for example, once every year, whatever, something like this. And then this smart watch will be able to monitor all different aspects of your health. And for instance, at detecting early stage diseases in order to prevent, the dramatic consequences of the diseases. So I will understand based on this talk that we really have a long way to go in order to develop platforms, computing platforms that can allow us to deploy such intelligence at the edge. All right. Let me see where is my mouse. Okay, fine. So how I will be doing this? I will start first with showing you some emerging applications and opportunities. What is the opportunity? Business-wise, if there's no opportunity, if there's no market, nobody will put money on the table. Quite simple. Everything you see in the community is mainly driven by business, right? And then we will see if there is an opportunity, which is the case, what are the challenges? And mainly what I'm calling hardware challenges, right? What are the challenges that have to be solved in order to make use of these opportunities? And after that, I will go to the computing platforms, give you a brief overview since the invention of the transistor in 1925 till today, and the production of the first chip, 1971 by Intel, the first microprocessor, give you an overview, a classification of the different computer architectures to highlight also what are the constant, the limitations to these architectures. And if we're going to enable new computing paradigms, what should we change in the architecture itself? And after that, I will go talk about a new computing paradigm called computation-in-memory. Explain it. What is it? How does it work? Does it impact the way we are doing things, etc.? And thereafter, I'll show you the potential of such architecture using real chips, real silicons. We have been, so in my department, we are not doing simulation only now. We make also chips in collaboration with our partners like IBM, like IMEC, like Acher, and so on. And I will show you some of the work we did in partnership with our collaborations, really show the measurements, the real silicon measurements, what kind of powerful result we can get when it comes to energy efficiency as compared with the state of the art. Actually, I had no time to put more results. We recently had 2 type outs in my department. So we made new 2 chips again. We are measuring them, but we have some results, but I have no time to put them in this presentation, maybe for the future. And finally, I would go and highlight what are the major challenges we are facing. Some open questions that keeps the community busy. Actually, we just got a new European project funded in this field together with different partners, including one partner from Morocco. So who we get on board? So one of the partners from this consortium is from Morocco. So we get about 10 million euro project in order further to develop in-memory computing, computation memory for each applications. So finally, I will conclude my talk. So what is the opportunity? So the figure on the left side shows you actually the exponential growth of what we call IoTs, Internet of Things. So think about any device you can put anywhere, right? Small devices. But when you think deploying this IoT together with what we call edge computing, we are really enabling a huge new market. Think about smart homes, smart agriculture, smart cars, so healthcare. Think about it, drones, anything at the edge could make use of these IoT devices. So this is an extremely nice opportunity which can impact different domains in the society, agriculture, intelligence, digitalization, health, and so on. So there is really a huge market opportunities. That's very nice. But let's go inside and see actually what kind of requirements, characteristics of this application. We have 3 examples there. We have autonomous driving, we have personalized health, and smart robots. So this kind of application that could make use of this, what you call edge computing, they have some unique attributes and characteristics. Let's start with attributes. They deliver a lot of data, what we call big data. They should be 24/7 online. Let's say, once again, if you have a wearable device for health monitoring, this device should give an alarm to your doctor anytime that the system detects something very dangerous. It's also environment awareness, security, of course, how we ensure that our data is secure, is private, etc. And also very important, energy constraint. We should not change the battery, for example, every minute. No, it cannot be. And therefore, we need to somehow to do also local computing. Coming back to real-time decisions, if you have an autonomous car, like the one you see here, actually, let me put the laser pointer. So this car, for example, we were talking about autonomous driving. This car has to monitor the situation and make a decision real time, right? And ideally locally, because if this system will send the information to the cloud, and if something happened with the communication with the cloud or the interconnect or the online connection, then the decision will be made late, and this could be impact the whole situation, could cause accidents. So doing real-time decisions should be supported for sure by local computing in order to reduce the latency. So this is quite interesting. But let's go about the characteristics. We have to do with huge storage. And when we say storage, we are saying memory. We have to do with energy efficient computing. That's a key component today. If we are not able to do computing, you cannot deploy it. I will come back to this later on, because again, AI has been there since 1940s. Research in AI has been there since 1940s. But when it never took off just in the last, whatever, 20, 30 years. And we'll see why. Again, doing computing is a very important component, but energy efficiency is another extremely important component. I will come back to this. And also your system has to deal with different data structures, voice, pictures, whatever. And also your system should be able to decide what to do locally in terms of computing and what to do remotely, which means what should I keep locally at the edge and what should I do in the cloud. This trade-off is very important in order to optimize the overall energy efficiency and still deliver the required quality, reliability, accuracy in the computing and so on. So if we really want to deploy, make use of this data, intelligence, whatever it is, we need two components. We need really to deploy an intelligence in appropriate way, so we need intelligence, but we also need an appropriate computing ecosystem. So let's go and talk about these different components, intelligence, and then computing systems. Let's start with intelligence. What you see in this picture is actually a graph presenting how does the machine intelligence over the years, starting from 2010, 2017, how does the machine intelligence changes and compared with the human intelligence. The horizontal red line shows you the human's accuracy, the human's error. And what we are using here as a case study, we are using what we call Imaginate. Imaginate is a project. It's a large visual database designed for use to visual object recognition using software research. So what you see there over the years, different solutions, different programs, and the key performance indicator we are using, or the metric we are using to measure this accuracy, is what you call top 5 error. It's actually the percentage of the time that a classifier, a solution, a software solution, did not include the correct class among its top 5 guesses. So a solution will guess 5 times. If it does not detect appropriately the image, then it will say it's an error, top 5% error. What you see now, the error started in 2020, started with 28% and starts reducing. And now you see at a certain time, since 2015 on, the machine intelligence surpassed the human intelligence. That's quite remarkable. Machines can do a better job than a human. That's really remarkable. But quite interestingly, what you see now, you see that this intelligence started in 2010. Why not before? As I already mentioned, research in AI started in 1943, where scientists tried to create a model for a neuron. In 50s, people tried to create a hardware which mimics the brain, kind of brain-inspired computer. In 86, the non-back propagation. So there was a lot of research, but we never deployed AI in real world. The reason is twofold. Number one, lack of data, because to deploy AI, convolutional neural networks, etc., you need data. And the second aspect, you need machines, you need computers, powerful computers. The most powerful computer in 1986, its computing power is today equal to a smartphone. So the smartphone of today is better than a supercomputer of 1986. So what you see is a revolution in computing power. How much computing can I do? And just around 2005, 6, when the single core of Intel, because you have a single core, because we could not increase the frequency of the CPUs, of the processors anymore, and Intel moved from a single to multi-core, where we can put different cores And multi-core means parallelism, and after multi-cores, we had GPUs, we have TPUs. So we had a revolution in hardware which could enable a lot of computing. And that's why how today we are deploying AI mainly in the cloud and servers, because we have big machines that can offer the required computing we need. And this is why you see it started only in 2010. And since 2012, we started using neural networks. You see different solutions, different networks, but interesting enough is how much effort does these guys cost us? Well, let me tell you another example. So over the years, the accuracy was improving, but accuracy means more computing. This shows you how much computing we need over the years. It's an exponential, actually, growth, because this scale is exponential, logarithmic. So you see that how much computing we need to make available has been growing exponentially. To give you an example, there's a well-known game is called AlphaGo. AlphaGo, it's actually a game, which is actually, it's a computer game, if you want to call it. And it was developed, I think, by DeepMind and later on sold to Google, if I'm not mistaken. So around 2017, this guy, JK, was by far number one worldwide in playing this game. And at that time, he played with a machine. So you have a machine, supported with intelligence, and this guy. And guess what? This guy, again, who was by far better than everybody in the world, this guy lost 3 times in a row against the machine. Again, this shows you that the intelligence of the machine is better than a human. That's always what we tell about AI. But the hidden part of it is actually how much resources we need. Let me give you an example. This is the machine that played against GK, against one person. We are talking about 176 GPUs. We are talking about more than 1,200 CPUs, all together consuming more than 150,000 watts. All of these equipments, all this big, expensive machine is played out against a single guy with a brain which consumes between 20 to 50 watts. It's not a fair comparison, obviously. And clearly, this kind of resources, you cannot make available for any application, for each application. Let's say if we're going to use smart agriculture, which is a big booming business now in Europe, actually worldwide, to deal in an optimal way with your water, with your resources, etc. So deploying AI for agriculture, each AI is very important. But obviously, we cannot afford so much resources for every application we can deploy. Just mission impossible. Hence, these kind of platforms are not suitable for what we call edge applications. Deploying AI at the edge at large cannot be done with the traditional way of doing things. So clearly the intelligence, the machine intelligence surpassed the human intelligence, but there is a major concern is the resources we need. Going now after the intelligence, going to the computing ecosystems. As all of you know, we can classify these computing ecosystems in 3 classes. Edge, sensors, edge, what you're going to do, you would like to deliver computing, and their efficiency. You want to do extremely low power computing. That's one extreme. The other extreme is the cloud, is the data center, is the services. We have these big frameworks, big machines, where you provide megawatts of power to run your computing. And of course, we have also to do with portable devices, with laptops, etc., which could be mid computing. But clearly, when we talk about edge computing, we have to talk about doing computing at the edge, at the sensors, at where data is generated. And this will be our focus. And the key question now, can today's computers, can today's technology deliver the energy efficiency we want for edge devices in order to be able to deploy AI intelligence and produce appropriate, accurate answers to our questions? Well, let's take a look actually on what's going on. Actually, this picture is created by one of my postdocs and it's already published in a conference. I don't know the conference, but anyways, it gives you the performance at this site. It is the state of the art, the performance in terms of gigaops, how many operations per second, and the watts, the power. This is all the leading edge device, leading computing engines, which try to mimic the brain. You see the TPU, the true note of IBM, the Loihi of Intel, and so on. All these brand new computing engines, which target neuromorphic edge AI and so on. What you see that at the best today, you can realize around 1 teraops per watt. We're talking about 1 picojoule per operation. Each operation you're gonna perform, it takes 1 picojoule. So this energy is again the key enabler. And if really we want to deploy AI at large at the edge, then we need computing engines that can operate at this stage. We are talking about 1,000 teraops taking tera operations per watt. Or we are talking about energy efficiency of 1 femtojoule, meaning actually 100x, 1,000x better than today's. If you take a look at this picture they took from IBM, they show their roadmap kind of. I'm not saying that IBM is too right, but just to give you a feeling what's going on in the industry. So IBM, this is actually you see again here the years, and you see the gigaops, the gigaops per watt, how many operations you can do per watt, kind of performance of your computing engines. What you see, these blue dots is what we have today in the industry. So they think if we want to really improve in terms of energy efficiency and therefore increase the performance per watt, we need to go to approximate computing, which means trade off the energy for accuracy. Let's say if we have an adder, and if we can do 3 plus 4, instead of giving me 7, he will give me 6. It's still okay for some application like video, imaging, etc., but not for all applications. And it's a known phenomenon today. If you can reduce your accuracy, you can improve your energy efficiency. But for the long run, what you see here, IBM predicts that for the long run, in order to get this 100 or 1,000x improvement, we really need to move to analog cores. So the computing should be analog, not digital as we have today. It seems this is a clear vision of IBM. And for the long run, to get to 10,000, 100,000x improvement, we need even to think about new materials, link the material technology, the material research to analog computing. So clearly, we need radically new paradigms, new materials, new computing paradigms in order to get to this 100+ x energy efficiency improvement, which we need to deploy AI at edge. Well, and the question is, can today's computing technology offer what we need? Let's take a look at it. So if you take a look at today's computers, what we call them von Neumann architectures, with this cartoon, I'm trying to illustrate how they work. So typically what you have a CPU. Let me again get my pointer. No. Boy. Okay. So what you see on the left side, you see the CPU is the guy who does the operations, and the memory where the information is stored. So to illustrate how the state-of-the-art computing, I'm using this cartoon. If I want to do just for simplicity, I want to do A plus B, a sum. Typically what happened is that your CPU will move the data from the memory to the register inside the CPU, move E, and then move B, and then do the calculation, and then move the result back to the memory. So typically, if you're going to simply do the same thing, what you see is you have to do with data movement. You move the data from the memory to the processing unit, to the ALU, to the arithmetic logic unit. Our brain does not work like this. In our brain, we don't have a memory separate from the computing unit. No, it's all together, right? So, but you can see, why should I care? Why do I care about this memory data movement? Well, let's take a look at how much energy they consume. Let's say if you're going to do this in addition, this is the Ali addition. How much it costs you? Let's say 0.05 picojoule. This is for 45 nanometer technology. Let's assume it's 1x energy. If you want to move the data from the memory, from the off-chip memory, it takes you 4,000 times more energy consumption. This is really crazy. The way I'm explaining to my students, I will give you 6,401 euro. Right? That's what I'm going to give you. To Hisham, for instance, Hisham, you get 6,401 euros. And they will ask him to do shopping, buy something, buy food. What Hisham will do, will take a flight, business class flight from Casablanca to New York, for which I will pay 6,400 euros for communication, for flight. He has only €1 left, and I will do shopping with €1. I will buy a piece of bread for €1. That's exactly what happened here. You are wasting a lot of resources for something that you don't like to do. You would like to do computing, and we are spending only 1x, and the rest is gone for communication. So clearly, this will not work. This will not work. We need a radically new architecture. Another component is technology, because if you're going to build a computer, you need an architecture. Like if you're going to build a house, you need an architecture, the rooms, the living room, the sleeping room, etc. But in addition to this architecture, you need the materials that you have to use to build this house, right? The same thing for the computers. We need a technology, device technology to build these computers. Today, computers are using mainly what we call CMOS technology. And there is something also fundamentally wrong with this technology. Why? You see here, these graphs gives you also the years and the power. The red is the dynamic power, the power you need to get things done. I want to do A plus B, how much I'm spending on A plus B. And this dark line shows you the leakage, the energy you are wasting without doing anything. Let's say if you have a smartphone, right? You charge your smartphone. If you don't use it at all, maybe 1 day, 2 days, the battery will run off, right? We are wasting energy even if we are doing nothing. And that's the fundamental issue with today's CMOS technology. You see here about, even though around these years, so Intel introduced what we call FinFET technology, it's a new device technology. It significantly reduces the leakage, but it's still about 30% of the dynamic power. So 30% you are throwing it away for doing nothing. Even though you do nothing, you are losing 30% of your energy for nothing. So fundamentally, we need to do something about it. We need new architectures, radically new architectures, because this phenomenon is the killer of data movement, and we need radically new device technology, because with this device technology, it's just impossible to realize it. I mentioned only one challenge for the architecture and one challenge for the technology. Actually, in reality, there are by far more, but I have no time to explain. Okay, fine. Now we know what's the challenge of the architecture of the technology. And let's see where we are standing. What are the different classes of computer architecture we have today? Again, I'm using this cartoon to do the classification. We have the memory core, as I showed in the previous slide, and the computation core. You can classify all computer architectures in two classes, COM and SIM. COM is computation out of memory. So this is the memory core. If you do the computation out of the memory, you call it computation out of memory. And it has two subclasses. Far COM, let's say a traditional CPU, you have the memory, you have the core. So we call it COM. And it's far because what is near memory computing, probably you heard about this hybrid memory cups, where we have DRAMs, memory IP DRAM, stacked through silicon vias on a logic layer. And we do the computing in the logic layer. So we don't change anything in the memory core, we stack it on the logic layer, and we do the computing in the logic layer. And all of this is in a single chip. We call it system in package. This is what we call near memory computing. Why? Because the distance between the computing unit and the processor is short. We call it near memory computing. So we have far and near memory computing. If we go inside of the memory, if we get the computing inside the memory core, like what you see here, if we go inside the memory, we are talking about in-memory computing. And of course, we have two flavors, because the memory has two parts. If you go inside the memory, we have the storage, which is about 70% of the chip, and we have the periphery. The periphery helps you to do the manipulation of data, etc. So if you do the computing inside the array, we call it SIM A. If you do the computing in the periphery, we are calling it SIM P. SIM periphery. Very important to see that when you do computation in memory, you don't need to move the data at all. The data is stored in the memory. You do the computation in the memory. You want to tell the memory, please do A plus B. The memory will do the computation inside and give you the result. Please do the matrix E times matrix B. The memory will do the computation and give you all the result. This is significant reduction of energy, because remember, I showed you this data communication is the killer. So if we are able to do computing inside the chip, wow, that's excellent. We can realize this 100 to 1000x energy efficiency. At least that's the purpose. And of course, we can have hybrid architectures. What you can understand that these are commercial architectures. CPUs, GPUs are far and hybrid memory camps are memory computing. And for SIM, it's mainly research and prototyping. And there is a lot of research ongoing here by all leading companies, you name it, Samsung, Intel, IBM, also foundries like Global Foundries, TSMC, everybody is working on these different flavors of technologies. Okay, so again, SIM, of course, reduces the data movement. I will illustrate with this cartoon again how SIM reduces the data communication. Again, I showed you before this. For this is traditional computing, the COM, you do the data movement, we know that. But if you don't know, and of course they are using volatile technology, CMOS, I told you CMOS leaks all the time, so we are wasting energy even though if you are doing nothing. If we do computation memory, I want to do A plus B, I will do now, please the memory do A plus B. It doesn't internally. More of actually, I can do parallelism. I can maximize the parallelism within the memory. The bandwidth is maximum. I can do A plus B, C plus E, D plus F, all at the same time. So, and if I will do parallelism, I will improve throughput, which is very good. So, inherent parallelism, no data movement, and if I cannot do, there is no data movement, and if I can use what I call non-volatile technology, instead of CMOS, use another technology, wow, that will be big news, because I can get rid of this 30% energy. That will be fantastic. But do we have this technology? The answer is yes. Again, if we're going to realize this, we'll be able to realize more than 100x energy efficiency. So, but do we have this technology non-volatile? Yes. Louis Schwa in 1971, he has a scientist who is still active. He's with the, what is this university in California? I forgot the name. Not Cambridge. Berkeley. He's with Berkeley. So in 1971, I saw this fundamental component of electricity. So the current, the voltage, the charge, the flux. And Louis was saying, you know what? There is a missing component here. And Louis was said, I will name it a memristor. It was purely theoretical concept that Louis was developed. He developed some characteristic, has two terminal device, he has this hysteresis, if you have the voltage versus the current. So has a memory which remembers the past, and you can switch it in different states. That was the philosophy. And the guy showed that you can develop two flavors of this technology, unipolar, bipolar. What is unipolar? You can switch the device on, off, based using positive, negative voltage. And if it's unipolar, you can use two positive voltage to change the states, or two negative voltage to change the states. The guy also showed the dependency of the frequency of the device. He did a lot of work, purely theoretical. From 1971 till 2008, it takes more than 30 years. In 2008, HP manufactured the device. They really made it in real silicon. And they showed, you know what? Yes, we can make this device, and therefore it becomes a reality. And since this date, many companies started working on this technology because it can enable in-memory computing and therefore energy efficient computing. So this is a remarkable change. Since 2008 till today, many companies are working on this. So it's really promising technology. And coming back, Hisham, how much time you have now?
If you can wrap up in 5 minutes, that would
5
be
minutes,
more.
okay, I will do that. So if you take a look now as in-memory computing, this is the memory, and in the memory we can do functions, we can perform functions. I can provide a digital input, I can provide the instruction I want, what I want to do, addition, multiplication, etc. And within the memory, I can do different functions. I can actually realize different functions in different memory blocks, and by doing that, I can get rid of what we call data movement. I will move now. I will not show you the electrical circuit design because we can do analog, we can do digital computing, we can do logic gates, we can do vector matrix multiplications in memory computing. Very remarkable. If you do vector matrix multiplication, for instance, theoretically here, this is an equation. You have a vector times a matrix. This is the equation. Actually, you need to do m additions, assuming that the size of the vector is m multiplications and m-1 additions. So the time complexity to calculate one element for this naive implementation is m squared. If I can do if I will do in-memory computing, I will do that in constant time, at least for this one of the time complexity of the algorithm. This is very important. But let me move ahead. What we did, we created some chips. And we have a design flow. We say, we will start with application domain. Let's say we're going to do EI. What are the requirements? What I want to speed up. If you are doing EI, you want to speed up the matrix multiplication. So I will define my architecture. I will do circuit design. This is the whole fly of chip design, from application up to the technology. Very important is we need a holistic approach. In the past, a software engineer, an algorithm engineer had no clue about a chip or a transistor or a microarchitecture. Today, you cannot do that if you're going to deliver high efficient energy computing. So we really need a holistic approach. We need the chip designer, the algorithm, the microarchitecture, the compiler talk to each other. And that's what we did in one of our projects. So let me give you an example. Let's say we would like to apply same architecture to database query. Let's say we have a database of stars. This is a data set, okay? And we would like to do the query database. For example, you have a different stars, A, B, C. This is the distance. This is the size of the star, large, whatever it is, and the year of invention. And I want to apply a query, find data which satisfies far or large. Find me in the database those stars which satisfies either far or large. We can map this data set in a bitmap indexing. And actually, if we're going to do this in database and apply in-memory computing, this will be stored in the memory, and this query will mean nothing else than doing a digital or far and large. And far is one row, and large is one row. If I want to do in-memory computing and I do this OR, I will realize it. So what is the requirements? I would like to do the kernel OR, speed up the OR. I will develop my architecture. I will do the circuit design. That's exactly what we did. And then I can do in-memory computing. Actually, we designed this chip together with IBM in Zurich, in Switzerland. This is a picture of the chip you see. We applied this on healthcare. We selected about 303 patients, which suffer from 41 heart problems. We created the whole system using in-memory computing, real chips, so real stuff. And we did database query. We sent 11 steps query. And we measured how much time. We needed only 36 nanoseconds. If a throughput of about 100 gigaohms. What does it mean in terms of energy efficiency? Remember, I told you energy efficiency is very important. We are talking about 6 femtojoules per operation. This is real measurements. Remember this number. I will come back to this in 1 second. 6 femtojoules per operation. We did the same thing for AI. For AI, what we need matrix multiplication. We did that using STT-MRAM manufactured devices from IMEC. We did the really measurements, etc. And what we did, we applied this for video recognitions. We did the matrix multiplications, which is the kernel for AI. What is very important to remember is this number. We find that we can do 11. We spend 11 femtojoules per operations. We talk about 6 and 11 femtojoules. This is what does it mean actually? If we can realize this with in-memory computing. Coming back to the same picture, the result we found fits right there. And that's exactly what we're going to hit. So indeed, this new computing paradigm, this new technology can get us there, 100x. And if this is a reality, again, where is my mouse? Boy. If this is a reality, come on. Boy. Unbelievable. Oh, good. I think We succeeded? No. Yeah. So if this is a reality, we will be able to deploy AI at the edge. So the conclusion is, yes, this radically new architecture using radically new technologies, although it's very high risky, it can take us to the second level of energy efficiency, as our example showed. To complete, but we have many challenges. These devices, they suffer from what we call non-idealities, variabilities, non-endurance, and things like that. And this could give us unreliable computing. So we have to think about how to deal with this variability. Other challenges at the architecture level, we need new compilers, new architectures, we need new tools, we need new communication protocols within the chip. But also if you have an application, how to map it, because you have an application, you need compilers, you need mapping methodologies. All of this should be done in order to enable a commercial solution of this kind of things. We need circuit designs, we need also ultra-low power circuit designs. We need also to deal with technology. We need actually to develop reliable devices. So many companies are working on that as well. We need to develop solutions to test these chips, because before you sell your chip, you need to test it. And also test technology should radically change, because these technologies are new. And of course, we need to deliver reliable devices. So in conclusions, we have many emerging applications which requires radically new chips. Yeah. Hence, we need to rethink the architecture, the design, the reliability, the communication, the mapping, the compilers, and so on. And what can enable this energy efficiency is the computation memory, new radically new architectures, learning from the brain-inspired computing, and the new device technologies. So I showed you clearly the potential, not based on simulation, but really based on real chips we made. But there are still many, many challenges, starting from technology, circuit architecture, but also what we miss in the community, we still don't have any full application. Usually what we show in the prototype, a small scale prototype. We would like to do a full application. And the project I mentioned to you, which is granted recently, and it's in which one of the partners is a university from Morocco, we would like to develop a complete full stack from device, circuit, microarchitecture, compile everything, and demonstrate a full application that indeed we can realize this 100 to 1000x energy efficiency. With this, I would like to thank a couple of partners like financial support from European Union, IBM, TW Aachen, IMEC, ETH Zurich, and so on, Eindhoven University, and so on. Thank you very much. I will be happy to take some questions.
Thank you so much, Professor, for the great talk and the provoking talk. This is very interesting. I think could revolutionize the state of the current infrastructure and architectures. So we have many questions, but for the sake of time, we'll just take a few.
Yeah, and the other questions you can send me by email. I can answer them.
Yeah, sure, of course. So first, we have a question. It says, while AI research is most commonly associated with advances in software, the performance of AI systems has been heavily dependent on the hardware upon which it runs, especially with the rise of deep learning. According to the Moore's law, the number of transistors on a microchip double every 2 years. Is this law still true or still stands? And how is this law related to the advances of AI, or specifically the deep learning applications?
Okay, so of course, Moore's law predicted that let's say the density of your transistor on a single unit will double every generation. Generation is, let's say, 1.5 to 2 years. This has been the case, but recently the Moore's law slowed down. If you think about what are the top companies that are really pushing for Moore's law, very, very, very few. They don't do it anymore because it's high risky. It's extremely costly, because when you manufacture a chip in 5 nanometers, I know I'm working with some companies. I can tell you the truth. Top leading companies, you can guess who they are. They are suffering to deliver high yield chips when it comes to 5 nano, 7 nano. So companies, they don't take the risk. That's one. And in addition to that, you have to deal with the extremely variability of your device. So the device is not digital anymore, it becomes analog. You have also to deal with the leakage. So there are major problems, and therefore companies are investigating beyond CMOS, alternative device technologies. The memory store I mentioned, you have the ReRAM, the PCM, the STT, the VRAM, the FIFET, are all device technologies that many companies are investing in order to push the technology beyond Moore's law, beyond CMOS, because clearly CMOS has limitation. And you see, actually, I can give you a clear indication. Our smartphone, if you think about the price of technology, since 70s till begin year thousands, the price of technology was going down, down, down. Today, the price does not go down anymore. A smartphone still costs 700 euros. Why? Because this technology is not becoming cheaper anymore. That's actually what Moore's law, Moore's law was saying, it's a cost, it's a financial model. If you double the functionality in a single unit, actually the cost should be reduced by 50%. This has been the case today, not anymore. Once again, because if you have a wafer, right? I have a wafer just in front of me here, because I want to teach, this is a wafer, I don't know if you can see it. This is a wafer, I don't know if you can see it. This is a wafer. And this wafer has, let's say, 1,000 chips. In the past, they can get 95% of the good chips. Today, they get only 60%. So they have to compensate for the costs. And who will pay this? Who will pay this is the customer. And this is why companies are not pushing hard for scaling. Hence, Moore's law is dying. Alternative technologies are being investigated. And I hope I answered your question.
We can take another question. It's about the energy optimization and green AI. The question is, how can we balance between high computing hardware that helps us achieve great performance, especially in the AI case and the applications, and the negative impact of these powerful computing systems that could have on our environment?
So, Hisham, if I correctly heard your question, let me rephrase the question. You are saying how we can create a balance between the energy we are spending on AI, especially in these big machines, and the green environment, that's sustainability, correct?
Exactly, yeah. And maintaining the performance of the models and applications.
So the whole world, let me, for example, take European Commission. European Commission, any project they finance in computing, they put this requirement on the top. So one way to do that, number one, is any design you're going to do, it should be power aware. You have to reduce your energy and power consumption. Actually, even though, why not? So there are many systems in field when they are running, they put them in silence. So the system should be actually silent, doing nothing, minimizing the energy consumption. Only if it will come in action. Like, for example, let me give you an example. Dynamic spiking neural networks. So like the brain, our brain works on spiking. Only if we need to do an activity, we spend the energy. If not, we're going to do nothing. So what you see also, even for traditional technologies, but also for imaging for sure, we need to spend the energy only when needed. So yes, the community, they are putting a huge effort to reduce. The effort is not enough yet, to be honest with you, because sometimes big industry, they care about the execution, about the performance. They don't care about the environment. Take a look at the China. They refuse to hear to these voices because they say we want to invest more, get our country to the top, and then we think about sustainability like you guys did in Europe and US. In Europe and US, 20, 30 years ago, nobody cared about global warming or sustainability. And so there are a lot of verses, but at least when we talk about Europe, they are putting a huge effort in putting sustainability as an integral part, not only in industry, in designs, but also in ethics within the education. Even though we got for engineering education, part of it, they teach the students how to think in a sustainable manner, how to make your design where optimizing the energy is just part of it. So yes, it's a very important aspect that the world has to take into consideration. In my view, we are not doing good enough when it comes to this aspect.
Thank you so much, Professor Hamdioui. We have 2 minutes left before the next session. So if we can just final thoughts on the infrastructure for a promising national AI strategy since this is the conference, and the final word on MoroccoAI and this kind of initiatives in Morocco.
So can you, I don't hear you. My question to me is how to build the AI infrastructure in Morocco and maybe about this initiative?
Yeah, I said if we can have your thoughts about how we can the infrastructure in building or creating a promising.
So actually, my view, I said it many times in many occasions in Morocco. I think without investing in science, technology, innovation and startups will not progress. Quite simple. Knowledge is the pillar of every developed society. AI is creating a revolution, if not already creating. I think the initiative is ideal, but it needs to get some support from important stakeholders, what they call control stakeholders, and if the influence of stakeholders. So I think it's a very good initiative, but I think it needs some support. It needs some vision. It needs to put a clear vision for and a clear mission for the future in order to be able to develop solutions to add to the society. And again, this can be in collaboration with some leading universities in Morocco in order to combine, to join forces and combine them to deliver what our society needs. Because again, as I already mentioned to you, Hisham, before the talk started, the knowledge, the universities, all this initiative I do see them as are responsible for developing solutions for the society. And I think this initiative could play a critical role towards this direction. So I fully support the initiative, and I think it needs more support, more discussions in order to you need also finance support, you need let me call them important stakeholders to support this. Just to be politically correct.
Thank you so much, Professor Hamdioui. Unfortunately, we got to jump to the other session. We still have other questions. We can take them offline. Thank you so much for your time, for accepting our invitation, and for the great talk.
My pleasure. All the best.